Okay, so this video is part 4 of exercise 4 in chapter 2 of the Advanced GIS book, topographic differencing. And in this particular video, we're looking at visualizing and beginning to quantify our vertical differencing between different digital elevation models. The image that we're looking at right here is the difference between 2018 and 2017 LiDAR data here along Diamond Fork and Spanish Fork area. And so it's colored, kind of stretched across the range of values in that difference, which range from uh, a difference of 17 meters positive to negative 8 meters in difference. And so across 1 year's time, shouldn't be expecting multiple meters of topographic change unless, of course, humans did something interesting. But 17 meters positive, I don't think there's any skyscrapers out here. So I suspect that most of that information, in terms of the differencing that we're seeing in this visualization, stretched across here is much closer to zero. And so we can confirm that by looking at the histogram. So if we're looking in the symbology for the data set, and you click right here and go to the histogram, and indeed we see the range of values here. And it is very clearly much tighter in, right, on this information right here, which must be near zero. Here's 17, here's negative 8. Most of the values are right here. Unfortunately, in ArcGIS Pro, these histograms aren't the best visualization um, tools. You have a little control, but not much. If we pop down the statistics of the histogram, we can see that the mean value is negative 0.15 about, or 15 centimeters negative. So why would be 2018 on average 15 centimeters lower than the year before? Uh, it could be potentially related to a better LiDAR scan with greater point density, potentially seeing under the trees. But I kind of doubt that there's a huge difference in these LiDAR data sets in terms of their quality. They probably spec to a similar type of scanner within a year. So I think there could be some other things going on. And I can actually see some of those things. If we zoom around the data, you'll notice a kind of square shape difference right here. If we click on it, it's negative 3 meters, right? And so this is actually a house. And so to kind of see what's going on with your differencing, you kind of need to see what the visualization products of your DEM look like. So here's the 2017 hillshade. And I'll turn now on the 2018 hillshade, and you can see the house has been cut out in the filtering of 2018, and it was there in 2017. And so that's why it looks negative right there. Okay. Now there's these two positive structures, those are cars. So maybe some of those balance out, but there's a lot more negative things because for whatever reason, the specs of the 2018 LiDAR did a lot more cutting out of things like this bridge right here. I saw other bridges cut out here, a building cut out there. Any of these blue kind of areas, building cut out right here, another one, another one. And so some of that negative is going to come from that. We do see, as we look across, potentially some contrasts uh, in aspect. So that on one side of a hill slope, it's kind of negative. On the other side, it's kind of positive. That could be due to tree differences and the amount of filtering, because there's more vegetation on one aspect than another in this landscape, and it could be filtered better or worse. But it also could be a horizontal shift in the data. Potentially, even a small horizontal shift will make things look a little different in terms of positive and negative values. So that's always something to be worried about. We could go potentially like to the riverbank to see if that is realistic. And interestingly, like if we turn on that, it's a little bit blue on this side and red on this side, kind of throughout. And so there probably is a slight horizontal shift. And so, um, that is something definitely to worry about if we were trying to use this to look at cut banks and things. Nevertheless, we can see a reverse in that shift right here on this cut bank. Whereas if the trend was that it should be kind of generally on this left bank, blue because of a horizontal shift in the data, then the right bank having blue would suggest there's definitely been real erosion there. Okay, so there could be some horizontal shift. We did use the same horizontal coordinate system, so it doesn't seem like that should be the case, but who knows? Are there other real things? So here is the area of what's called the Schertz landslide, and we can see some effects there where it does seem like we might be seeing some geomorphic activity on the edges of the earth flow over that year. But again, it could be an aspect thing. And here's a channel neutral kind of in the bottom and slight shifts on either side. Interesting. One place I was pretty sure we did see some real change was right here. All of this blue, which means erosion over that year, seems consistent on either side. And in the middle, there might be some deposition. And so if I turn on 2018 hillshade, can see that is a channel. And so if there had been erosions of the side of that channel, might expect a little deposition in the middle and deposition down below, which we might see here. Let me show you 2018. Now turn on 2017. And I can sense a little, like we were talking about, that potential shift. But also, if we just look at the general shape of that channel, it does appear wider on both sides in 2018. So there's probably some real signal there. And so it does begin to show you some of the power of this topographic differencing. So if this histogram was a little unsatisfying, there are some other types of histograms. You can go into create chart, histogram. You can even export that information, and that's probably the best way to go is to export it and bring it into another program that pixel data and create your own histograms there. Yeah, okay, so now how do we visualize these topographic difference images in a slightly better way? So going over that whole range of data is not really realistic. So if you want to customize your histogram stretch, you can do that. Go to a custom stretch. You can tell it that you only want to look at things nearby 0. -2 to 2 might be a good range for kind of more realistic values. And at least in the symbology sense, it doesn't really change the visualization too much, but at least the symbology is more likely close to true. If you really want to get the symbology true, then I would recommend doing classification. And so what I've done here is I've copied this and pasted in and called it classified. And then I have gone into this symbology right here, and I've given 9 classes, 4 on either side of a central neutral area within plus or minus 10 centimeters of zero, I called that no change. And then as it went to cooler colors, it was negative. And it went to warmer colors, it was positive, uplift. And then I went in small demarcations, so like 10 centimeters to 25 centimeters, 25 centimeters to 1 meter, 1 to 2, and then 2 to the end. And so then that kind of classification is a little bit more effective, in my opinion, for pointing out things like houses and bridges that were kind of cut out in 2018, and then maybe piles that actually are real things that were put there by humans and since 2017. And you start to sense some kind of fluvial kind of shapes in the floodplain that might be showing you some magnitude of signals that could be true. Fortunately, the stream generally looks neutral, so there wasn't too huge of a change there. Yeah. And so if we then take that over to the landslide, does seem to show some bit of deposition in some little areas, but generally it's fairly neutral in the landslide itself. But on the levees, it's kind of more in this 10 to 25 centimeters lower realm. And it's interesting that it's across this whole kind of uniform slope, kind of like that. And so it does tend to speak a little bit towards vegetation. I do know that this side of the landscape may have burned around this time, but that doesn't explain why we see similar things over here. A few other weirdo things. This is kind of on the edge of the data, so I'm not sure what to think about that. Some really high blues up there in that topography. And then in this weird landscape right here, we do get areas of big erosion and maybe deposition as well. If we look at what that looks like in the hillshade, we can see that's really steep, kind of real like topography and bedrock. And so you could have blocks of potentially erosion off of those cliffs if there had been kind of some big things moving around. Also, with things being really steep like that, if there's a slight shift, that could be responsible for it. But given that the shapes are not all exactly parallel to one another, I'm not sure they're all due to that. Yeah, so hopefully this is helpful to have seen an example of how you might classify the imagery to visualize things a bit better. And that's how I would almost always do it with these vertical differencing data sets, is do the classification. I might start with stretch, custom stretch, so it's just narrowing in on the low values, and then move to a classification, giving yourselves a lot of classes around zero, and then maybe some fewer classes as you move out from there, and keeping your classes kind of logical. So all kind of warm colors on one side and cool on the other. So what else can we say? So I want to back out a bit and think about what else that we see if we looked at some of the other difference maps. I know we looked at these briefly. So this was the difference between 2018 and the 2006 photogrammetrically produced data set. And in there, I think we see a lot of structure from roads and vegetation. And generally we see it's not particularly useful. We might see some of the same things like the erosion along this edge of the road here. Weird things going on in this kind of rilled bedrock landscape. And you kind of sense something going on in the landslide itself, as if there has been movement with time there, um, and deposition in some of these levees. So potentially there is some utility to differencing these data sets, even though they're both not digital terrain models. One is a DSM and one is way worse in terms of its resolution. But yeah, you got to take those limitations into consideration. And then finally, looking at the ALOS 30-meter difference, it is not very useful. Primarily, the signal that you see is that those 30-meter pixels, and how they've been averaged. And so one side seems low of the pixel, the other side seems high. And you can see where channels run through the landscape and roads. And so this is not particularly useful. And so I wouldn't try probably ever to difference these hugely different scaled um, DEMs. But if you were interested, you could always potentially try to difference two similarly scaled regional digital elevation models, such as SRTM, which was collected in 1999, and then the one that was collected a little over a decade later in the ALOS, especially if there's been a big landslide or something in the area and you want to kind of get a rough estimate of that motion. But yeah, these pixels are just too contrasting to see a lot in that difference map. Okay, so let me just review my notes here. So we've compared things visually. We've compared things using histograms a little bit. Again, to do that better, what I would recommend you do is go into Create Chart, Histogram, and then I believe, is it from here? Well, what I would recommend is basically finding a way to export all of the data and into another program and adjust your histogram that way. That being said, if you wanted to see what was going on in some particular area, uh, there are some mechanisms to do that. We could basically, we see this potential lowering of the landscape right here due to rilling along the edge of this roadway here. And if you wanted to know kind of the rate of change over a year, you could calculate what's happened here and divide it by time by pixel. So, for instance, you've got you could basically kind of just mask this area and analyze it. We could also do kind of what's called zonal statistics. So, for instance, if we said over, the area of this rill, what's gone on, we could go to geoprocessing and we could go to create a mask. This is a little bit of a hack of a way to do it, But you could say, okay, I can see that there's been erosion in this area. I'm going to go to the 2018 image. And if you kind of just said, okay, we kind of follow the edge of this thing, and I'm only going to do the side that's the part of it that seems to have eroded. So not down below. Because now I have this little mask, right? If I go back to um, I go back to the spatial analyst tools, there's a toolbox called zonal, and you can do zonal statistics. So I can enter that little polygon, and um, and then I input the difference value raster, and then spit out statistics. Actually, this is, let's see, zonal statistics as a table. Let's do it that way. So and I'll spit out all statistics. So this is going to create a little table which shows me, oh, where did it fail? Where? Well, so you need to, so if you have a feature or another raster, you are supposed to be able to input, let me just change this to object ID and try. Yeah, that was it. It didn't like the name. And it'll spit out a table which tells you what's gone on with the pixels in that area. So in that table, we can see that it's an 433 square meter area, where on average, based upon the polygon I drew, erosion over a meter has taken place by each of the pixels. But there's a pretty significant standard deviation across there. But a meter of change on average over this area shows a lot of enlarging by rilling, and that's not something you'd really want on this huge embankment on the side of this road. So it shows a significant erosion event is taking place there. Could some of that be to that horizontal shift? Potentially, but this is pretty interesting. You could, for instance, figure out the volume of that house if you wanted to with this sort of thing. We could do other things with zonal statistics. For instance, if we knew that we had a good result, we could, look across the entire floodplain and say, has there been on whole, could like make a polygon across that floodplain. Has there been on whole erosion or deposition in the floodplain? And you could do that segmented, like in different reaches of the river to know what's going on. It kind of looks like maybe there might be deposition down here and might have expected more erosion here. Things like that. If you wanted, you could spy on your neighbors. How much dirt are they moving? things like that. And so zonal statistics can be quite helpful. Another tool that we can use is profiling of any of these rasters. Okay, we can profile the difference map. We can profile the elevation data itself. And so to do that, there is a tool. If we go to map and we click add data, what we have to do is call these things elevation source layers. So we have to go into our project and we have to point at the data sets that we're using and add them as elevation source data. And so I'm going to add this difference map, and I'll try to add the other ones as well. So like the clip LiDAR reclip 2017 and 2018 if possible. So now I have 3 elevation source layers. I don't know why ArcGIS does these as separate layers, but they show up down below here as ground layers. And so then if you go to analysis, there's this tool called exploratory 3D analysis. You can do an elevation profile, check your units. All our units are in meters. And then, well, I've got them all selected. Let's see how that goes. I don't know if it'll let us do that, but let's just go back to our funny little rill. If I'm profiling across it, which one am I profiling right now? I've profiled all at once. Okay, good. So here's the difference map. It would be nice if they were all right on top of each other. And so one thing you can see right here is that there's a uniform difference across the bank where it's uniformly lower. And we talked about that already. And so that's probably part of the signal that's not really real. But then you see this, boom, 3 meters down in the center of the channel. And up to 0 here and some more erosion over there. And so then if we put back 2017 on here, okay. So 2017, the peak channel is over here. It's kind of wide. And the edge of the channel is there and there. So we can already see that something's going on. And in 2018, it's much more smooth and laid back. It's wider all the way over to here. So at 10.25, we go back here, it's not starting till 11.8. Its peak is at near 14.9. So there's definitely feels like some horizontal shift has taken place in the data a little bit too. But that could be, erosion coming down across here. Why is it so much smoother is another question. In 2017, it looks a little bit more realistic. But remember, the 2018 data that I downloaded was a 1 meter data set. And so it has been smoothed a little bit. And also we then kind of forced it to be half meter and might have smoothed it a bit more there. So yeah, topographic profiling can be informative. It can also show you, let's go somewhere where we're not sure there's been real change. So let's turn on So right across here, I wouldn't suspect that there's real change going on. And so I would like to see if that drainage position has changed. So again, we just interactively replace, a profile across here. And hopefully I had all those selected again. I did. So if I turn on 2018, there it is. The center of that channel is at about 19 meters. And then here it seems to be also about, here might be a little bit further, like a half meter over to the right. And so some of this shift could be related to that smoothing and kind of difference in resolution. So be careful of that. But then we can see that all across here, negative values. And then boom, up over here, all positive, although up and down a bit, right? And so, interesting. If everything was shifted half a meter in one direction, you might expect to see something like that. So it does make you a little bit worried about that. So profiling can be an effective tool to help look for what's real change versus not real change. We go across, for instance, the river banks here. Erosion is supposed to be negative. And so let's do another profile, this cut bank right here, which also does look negative. So what am I looking at here? So this is the difference. So erosion right here in this cut bank. Off of the cut bank, it's uniformly low 10 centimeters. So probably the real erosion is between 10 centimeters and whatever this is, 0.6. So half meter of lowering down to the river channel here. And then in the channel, the river, the water, not much. But now we get maybe out of the channel, we're probably up on a point bar here, it looks like. And here doesn't look like any change, but maybe since it's 0.1 was uniformly lower, it's a little bit above 0.1, that could actually be positive, even though it doesn't, it looks a little negative. And then for some reason, they have some erosion up here. That would suggest that water flowed over the top, right? And cut out a channel there. So potentially profiling could be useful for this sort of stuff. Okay, so I think that about wraps it up. So we can quantify things in one dimension along a profile, up or down. We can quantify things over areal shifts by using zonal statistics and polygons where you're interested in what changes have taken place. You could translate those into volumes, height times width, if you wanted to. And then how do we visualize things? Again, you can stretch them, or I would recommend classifying things. That's a little bit better. Of course, to do things really well, we want to be sure that our vertical datums are correct. We know that they were the same vertical datums for these two LiDAR data sets, but we seem to have some sort of question about whether the data sets are truly aligned in a horizontal sense here. And so that is kind of playing a role of uncertainty in these results. And the large signal that kind of tells us that is the kind of almost like an aspect shift. One side of the hill is one color and one side is the other. One's the negative, one's positive. So what this is almost like a hill shading effect, right? And so if you do a difference map and you get a hill shading effect as the default output, let me show you. You should be a little suspicious about a horizontal shift, giving you apparent vertical change. So I'll switch. Come back. Okay, so there it is. So this is just a grayscale difference map. And it looks like a grayscale photograph of the landscape or a hillshade model. When you see that, you should be a little suspicious of horizontal shift, in my opinion. Yeah, so just be wary. Okay, yeah, we'll stop there. So this end up having only 3 videos across this tutorial. And so hopefully this helps you get going in your second lab of the semester doing topographic differencing across an area with more clear differences due to groundwater pumping and subsidence and negative topography down in southern Utah. So hopefully this has been helpful. Take care.